So, good afternoon. Today I will be presenting you an admittedly somewhat speculative future vision of a future in which I see a merging of an old world, which includes type traits and compiler intrinsics, with the new world of static reflection, which is coming up in C++26. So first things first, my name is Andrei Zissu. I've worked in multiple industries, in finance, in cybersecurity, even in multimedia over the past 2 decades. I mostly have done my work in C++ on Windows. Currently, I am team lead at an Israeli cybersecurity startup called Morphisec. The thing we do is called Automatic Moving Target Defense, AMTD. It does a kind of scrambling of system resources so that an attacker, if they do get in past classical defenses, they will just be unable to find what they're looking for. And to top it up, we will also usually catch them in the process. And we are focusing on the anti-ransomware market. I've been a standards committee member. It's soon going to be 4 years. Mainly focused on the reflection and contracts. And as I say, this is a somewhat speculative, and I'm presenting my opinions here. This is going to be a somewhat opinionated talk. I'm not presenting either my employers or the committee's opinions, even though I do hope to move them in time towards this direction. What we're going to see, I'm going to cover the general idea of type traits. And I'm going to tell you how this idea I came on while reading committee material, and which got me to ask a question. I kind of saw lots of overlap between the current type traits and the future type queries in reflection. Which got me asking whether type traits, which are currently mostly implemented via compiler intrinsics or built-ins, can be re-implemented via type traits in a portable manner, which would allow us in the future to start cutting the cord between compilers and standard library implementations. Right now, the two are very strongly coupled together. And I went as far as making a proof of concept, which kind of shows that this is indeed possible. A quick introduction of a few basic terms. First of all, there's at least one person in this crowd who will correct me in the fact that I do choose to use intrinsic and built-ins and magic as the same thing, even though they are not exactly the same thing. But I find it comfortable to intermix them. The thing that's important to me is that these are things that are intrinsically non-portable. Whatever they precisely are, they are the non-portable things that I aim to get rid of in standard library implementations. Now, the type traits I'm mentioning are quite a basic building block of things that are currently in much use. The type traits themselves and standard concepts, which are mostly built on top of those type traits. They are in wide use in all sorts of code that needs to know things at compile time. The coupling I was mentioning, you can see here the 3 big ones, the Clang, GCC, and MSVC, each with their own library with some cross support, but in no way is it everything supporting everything else. Those intrinsics, or rather in this case the built-ins, I hope I'm correct this time, are a kind of a gateway towards the internal world of compilers, which typically would have an abstract syntax tree, an AST, and the intrinsics usually make this accessible externally. And in large extent, this is also what reflection will do. Quick intro to type traits. So we see here an example this is relatively modern code, which uses if-const-expr. If-const-expr is the compile time form of if. Obviously, it's only usable in template functions. It creates an instantiation of whatever if clause matches. Only one of those if clauses would actually be compiled into that template instantiation and be available at runtime. We can see here the uses of type traits. You can see type traits as a very first way which was introduced in the 90s of doing so-called compile time meta functions. You can do quite a few ways of logic in quite cumbersome ways at compile time. And we can see here the first if-const-expr clause in this function will only match integral types. Is-integral is a type trait. It will match multiple types, all those that are obviously integral. Or we could be matching floating point types, depending on what t is. Same for pointers. And anything else will go to the else clause and type this default message. The old way before we have if-const-expr, was using things like enable if. Enable if does kind of pattern matching. You can see this as, they say rightfully so that C++ is a multi-paradigm language. And this is one of the paradigms it supports, even if it's not officially so, which is logical programming. So we have this kind of pattern matching. I think there was recently a talk about the old pattern matching we have ahead of perhaps one day we'll have actual pattern matching in the language. And this is it. We match patterns via templates. And here we don't have if-const-expr. We can't pack it nicely inside one function. So we will match only one of those functions. We may match more than once, and then we will wind up with a stronger match. If we have a tie for the stronger match, we get a compiler error. The thing it's looking for in this match is the present. In case of is integral, this is kind of Boolean predicates. They will either they will have a value field, Boolean. Enable if its template parameter is a Boolean and its so-called result of the meta function is a type field. If the meta function failed, the type field will not be present. So we're looking for the type field. If it's present, it will be t. So we can see here we have is integral. Above it we have enable if, and we have our query here. And we are also looking this time in a separate function. Those are not overloads, those are template instantiations. We're here looking for is floating point, the same way. And we have somewhat more modern code with step helpers introduced in C++ 17. And you can see here the syntax is now somewhat shorter. Instead of looking for the type field, we have a helper with underline T. And instead of the value field, we have underline V. So this is nicer to write. We have, in terms of this kind of type traits, the Boolean queries, we have some of them are unary. You can ask, for example, if a type is const. And some are binaries. Same, he's looking for equality between two types. We also have what I call, I'm not sure what the official name is, I call it the type transformation or transformative type traits. They take a type trait and produce another type trait with that transformation. This is kind of, if you think about it in terms of logic and functions, kind of reminds you of value semantics. There was one such talk yesterday. Now we get to the current implementation strategies of standard type traits. In general, there are two strategies and a lot of overlap and mixing between them. there are the ones that I'm mostly aiming for, but not only, the ones that are based on built-ins. And there are the ones based on templates. Now, the one based on templates are on the face of it portable, but they do have their own issues. And as I said, lots of mix-up, including many type traits which use both strategies. Now I'm going to dive into the template-based implementations. There are a few basic building blocks. The first one you've already seen, enable if. Another one is integral constant. At its base, integral constant is a struct template. It wraps a compile time value, which is passed in via NTTP, non-type template parameters, which, by the way, the new C++ 26 standard will refer to this as constant template parameters, just so you know, to make things just a little bit more confusing. There's more to this implementation, but this is really the important part. We have helper type aliases here. You may have encountered true type and false type. This is what those are. They are instantiations of integral constant. And we have another instantiation, which, unlike the first ones, is a partial instantiation. Which is known as bool constant. So bool constant can be either true type and false type. The whole idea here is to have a Boolean value which is forced to be available at compile time. Now to enable if, we've already seen how it's used. Let's see a little bit about its implementation. We have a base, the primary template, that's a base case. Everything will match the base case. And then we have a specialization. A specialization, if it's matched, it's always considered a better match. So a specialization will only match a true value. And if we get a specialization, we get our field, which is a type def. Type def and T is mapped onto it. Otherwise, in the base case, we don't have it. And we have the helper type alias that we saw before. It's quite easy to figure out how it's implemented. And all of this works by the so-called and horribly named SFINE, which stands for substitution failure is not an error. It's always nice to witness Bjarne in person apologizing profusely for this naming. But come on, the guy was young back then, so young people make mistakes. So, in terms of usages, just a quick reminder of what we saw before. By the way, we see here two calls to the print function. Each of them resolves to a different instantiation. In terms of the other helpers for the Boolean queries, those are implemented via variable templates. Other than this difference, they're also trivial, as you can see. I'm not sure how they were implemented before. Variable templates were introduced relatively late, I believe in 17, but yeah, they are available now. Now we go to type trait implementation, starting with those which are implemented via templates. So this is, in this case, about templates and not about built-ins. Here again, we see the strategy of having a primary template. Everything will match to it. In this case, we are looking at the GCC implementation of isNullPointer. IsNullPointer needs to match all the various incantations of nullPTR. Why do we need all of those? Because unlike overloaded functions, in templates you need to have a precise match. Thank you. So, we see here the first match. We are matching null PTRT as is. Then we are matching it with const and with volatile, and then with const and with volatile. In all those cases, we are inheriting from true type. So we'll have that true field. The value will have the value true. In the base case, we are inheriting from false type. Now we see another slightly different strategy. Now we have a public face, the public trait, the public facing one is signed, is implemented in terms of an internal helper. The internal helper has the base case. We are seeing here, we are seeing here the GCC implementation of is signed. So we see that the base case, this is going to match everything. But the second template parameter is going to be initialized by default, and we're not providing anything but the default. It's going to be initialized based on whether the type is arithmetic. Arithmetic is, of course, not a type trait. And in case we get a true value, we are going to match this instantiation of the helper. And then we are going to derive from some form of Boole constant, which is presumably more or less equivalent with the normal Boole constant, instantiated depending on the value of this, simple equation. And we are getting our result. Remember, Boole constant initialized with true or true type or false type is the same as the other type aliases equivalent with it. And we have the variable templates. Now we can see this is the usual case we've seen so far. We have the implementation of the trait itself, and then we have the helpers implemented on top of the regular one. But there are also opposite cases. We can see in this case taken from MSVC of its const, we have actually the helper is the one where the actual logic is being implemented, again in a very trivial way. And then we have the full type trait implemented here in terms of the helper by instantiating a Boole constant with the result of the helper. And now we get to the main topic of type traits implemented via compiler internals. What you're going to see is all sorts of samples I've dimmed in a non-scientific way to be more or less representative of what I saw in the various implementations. And each such implementation uses their own intrinsics, as would be expected. We can see Clang, the Clang implementation of its const. And one thing that we're going to see many times moving forward is that we have alternatives here. This is intended to also support old versions, and in many cases to also support other tool sets. In this case, we can see that it's looking for the presence of the isConst built-in. And if it's not present, it's still able to produce a template-based implementation. We can see that in this way, it is able to achieve, if it's willing to put in the effort to achieve interoperability. But you can imagine how much maintenance it would take, especially if they want to support more than one foreign compiler. In other cases, they didn't bother with this. They just use the built-in, and if it's not available, neither will the type trait. Here is the case here as well. Several type traits which are implemented only in terms of built-ins. This is from GCC. And here it's, I find it a little bit interesting. We can see here, again, we do have both alternatives. And the thing that strikes me here is that both are quite simple. Admittedly, the template-based implementation is a little bit longer because it needs to handle several cases, but they're all one-liners. So why bother with the internal? And this kind of gives me a hint that no one likes doing this with templates. Perhaps here it's not about maintenance, but think about the build times. And we can see in this case, in MSVC, they are kind of all over the place here. All of those are implemented in terms of internals, but some of them are using a struct, others are using a variable template. I have no guess how they made this choice, but it kind of, I don't know, seems to me like a lack of concrete methodology. And we can see quite an interesting thing here. We see here an MSVC implementation of isMember function pointer. Now, MSVC supports Clang. You can change your compiler in MSVC and compile with Clang. So their standard library implementation needs to support Clang, including its intrinsics. Actually, it loves the Clang built-ins. It loves them so much that it prefers using them. So in this case, if we're compiling with Clang, it's actually better because we're going to use the straightforward built-in. If we're compiling with Visual Studio, with MSVC, we're going to use a template-based instantiation, which looks quite simple, yeah, until you pay attention to this line, which delegates to something, and that is that something. And this is a simple something, which I just needed to minimize the font a little bit to get into one screen. So kind of what I picked this one in particular. Yeah, so as you can see, the template-based implementations are quite complex, seemingly, especially Microsoft. So the next thing I did, again, not in quite a scientific way, I just followed some implementation, so what leads to what, and whether I ultimately end up with a built-in or with a template. And I put this in some dot files and run graphviz to get this kind of thing. Now, don't worry, I'll zoom in a moment. So I'm starting with MSVC. The things you see here, on the left side, there is a blue circle. That's my template nexus. And the red one to the right is my red nexus. That's kind of base nodes where the respective implementation end up. If you see something ending up in either of them, you'll know what it's mainly based on. So this is the tangle mess that is the MSVC template implementations. You can see here lots of layers and lots of complexity. By the way, even here, the lower ones, you can see are underline something. Those are intrinsics. Those two words are never completely detached. And there are also arrows leading further to the right. This is the connection point between the two worlds, so you can see they are connected. But you can see the complexity here. Now we're getting to the good part, the built-in based one. So here we no longer have that kind of complexity. And now we get to Clang. This looks much better. First, you can see how much to the left is my blue nexus. A little bit more, it would have flown off the screen. So that's they have very few template-based implementations. And even that part is almost as shallow as the rest of it, the built-in based ones. This looks like some orderly thing. Again, the lower level is already built in, so you basically have only 2 or 3 layers. This is entirely reasonable. And yeah, it looks like built correctly. And we're done. We're already in built-in territory here. We have lots of built-in territory. And we have GCC, which is somewhere in the middle. From what I managed to dig up, GCC probably started up quite similar to Microsoft. And they've ever since started gradually migrating to the Clang way of doing things. And now they are somewhere in between. Yeah. So we can see here the focus on the template-based GCC part. Those are more complicated than Clang, but not yet as what we've seen with MSVC. And the rest of it, same as we saw before, simple built-in based layers. Some comparisons of those graphs. We can see Microsoft, the blue circle is way to the right relative to the other ones. The opposite is Clang. And we have GCC somewhere in the middle. Some things worth knowing about how I approach this building these graphs. There are many cases where there are alternative implementations as the one I showed you. I ignored the template-based ones in these cases because I'm looking only at future standards where the built-ins exist. So I don't need to care about backward compatibility when doing these comparisons. Of course, I'm looking only on type traits because I'm interested in portability, not in vendor extensions. I mean standard type traits. I've simplified some details. There are lots of intervening templates which don't contribute much to the overall analysis. I've covered, I believe, more or less half the standard type trait. I do intend soon to complete this POC and perhaps produce a paper about this. And of course, humans are known for making errors. As I mentioned before, there is cross-toolchain support, but only in the limited way that implementers choose to provide them. We're nowhere near being able to mix and match anything we want to. MSVC supports Clang. The Clang library supports GCC. I haven't looked into GCC, but from what I've heard, they seem to support all the 3 other ones. And I heard yesterday from the same guy here in the crowd that Clang even went as far as supporting GCC built-ins in the Clang compiler, which, I don't know, to me it seems quite a crazy thing to do, but this is exactly the thing I'm talking about, how far people are willing to go today because of those couplings. So, the problems with the current type trait implementations. They're complicated, good luck reading that code, perhaps AI can help explaining it. They are built in a logical programming style, which is not as bad, but you do need to wrap your head around yet another concept if you want to maintain them. So overall, it's quite clear that they are not very easy to maintain. And those compilation errors when you have problems with templates. This is one of the reasons concepts were introduced in C++ 20, but I believe most of you know that only do a partial job in simplifying those huge error messages. So we're not there as yet. And I haven't measured it, but from all our experience, it's quite clear that heavily templated code is going to be producing long build times. And there are also, in terms of maintenance, which I've mentioned, I believe it's particularly difficult in the cases of composite type traits, things like isScalar, which need to maintain a list. So isScalar is made up of isIntegral, isEnum, isFloating point, and so on. And each of those has its own list. And every time something changes in the language type model, this needs to be maintained. Someone needs to remember to maintain this. So I don't like this in terms of maintainability either. And there are some cases where there is no way to implement those traits other than via built-ins or intrinsics. Isimplicit lifetime is one of those examples. And this will be implementable given a proper reflection endpoint. If there is no such a reflection endpoint, of course, it can be added via a paper to reflection. Now it's time we talk a little bit about static reflection. So first of all, the word static. Static is one of the most abused words in C++. We think we always miss we'll feel the lack of enough uses of this word and always look for new ones, new uses. In our case, static means compile time. And this is different from most other, actually I'm not sure if there is any other language which has compile time reflection. Usually they have dynamic reflection, by the way, same with templates. Most languages which have generics will have them at runtime and we have them at compile time. Okay, so this is about static. As of the current state, reflection is approved for C++ 26. The flavor that was approved into the language is so the so-called value-based approach. I'll talk a bit later about the alternative. The things it supports is introspection mainly, means you can analyze the code. You are quite limited in the types of code you can produce. So it's mainly reflection in the actual grammatical meaning of the word that you can reflect on yourself. There is some things you can do, such as, and which are very relevant to this talk. We can splice in several kinds of entities, including types. You can take a type, make some manipulations, and produce a new type. And there is also something called define aggregate, which allows you to add public members to structs. There is no way yet to produce things such as code or to reflect over expressions or code. The AST cannot be modified. You can produce a node. The moment it's reified, that's the technical term, it's added to the AST and you can no longer modify it once added. And it uses value semantics in the way I hinted to before, that you produce something, you don't modify something that already exists, you produce something new. Along with reflection in a different paper, but very usable for reflection, although obviously not only, we are finally getting expansion statements, which you'll see in code in the form of template 4. Template 4 will allow you to iterate at compile time over compile time entities. So it could be iterating over all the values of an enum, It can also be iterating over all the structs of a tuple, for example. And this will not translate to a for loop at runtime. It will be unpacked. But instead of having to write duplicated code by yourself, you do a compile time template for, and you're done. Okay. Now about the value-based reflection. This is the value that's being referred to. Reflection will be based on this opaque type, stud meta info. The reason it's been done this way is to be future compatible with changes in the type model. The other proposal would have been modeled around the existing language type model and would have needed to be maintained. So there's pros and cons to each of those approaches. Myself, I fully understand the motivation. I also do think that right now it's quite difficult to use, and unfortunately I believe that in 26 it will be a mainly expert feature, albeit a very usable one. And I do hope, perhaps I can help with it myself, to also have some standard library edition to wrap this interface and produce that type-based model that will make it much more usable, even if it will require more maintenance along the way. Now, stud meta info, this is somewhat reminiscent of the way null PTRT is defined. Null PTRT is defined as the type of null PTR. Here, the standard won't mandate this, but this is the suggested implementation. Meta info is a reflection of anything. Any reflection you do, you will wind up with a meta info. So the simplest way, perhaps, to get it is to reflect over the global namespace. So this is the suggested implementation, therefore. We can see here the way to obtain a reflection. We'll see the reification soon. The way to obtain a reflection is this caret caret. It used to be a single caret, and then people pointed out that it created some ambiguities. So now it's caret caret. So you'll be glad to know that that after we got the spaceship operator in C++20, now we, of course, unofficially also have the unibrow operator. I don't know if I can do this. Yeah, that's the fun name of this thing. I won't go over this. This is the list in the paper of the things that are currently being supported. If anyone wants to take a picture, this is your chance. Otherwise, just open P2996. That's the paper. So we can see here the unibrow operator producing a reflection. And we have, this is the so-called splicer, the reifier. And there is a error. They probably got it from the original paper that I took screenshots from. The actual operator is symmetric. So those slides are missing the first colon. So keep that in mind. So the splicer does the opposite of the unibrow. So given a reflection, we will get that entity that was reflected over. So in this case, we get back the type int. And we can see here, we're going both ways. We're reflecting over a char, reifying it, we're getting char C. Here we can see we have a struct, and you're going to see lots of these const eval functions. All this stuff can only happen at compile time. So if you write a function to make such a production, there's no point ever running it at runtime. This is a pure compile time function, so therefore it's defined as const eval. And we can see it takes an index. And if the index is valid, it will give us a reflection of that member of struct S. Otherwise, we will flow off the function. Flowing off a function in C++ is undefined behavior. And then this only happens at compile time. We will get ill-formed code, which will probably manifest itself by an error message that says this is not a constant expression. It might be a bit confusing at first, but this is what it means, that you did something wrong in this kind of logic. Okay, you can see the usage. So we are using the result of the function. The function returns a reflection. We said const eval auto, but what's returning is, of course, a meta info. We are reifying it, and then we can apply the result, and we write s dot, and then by reifying this, we get the field, as if we had typed the field name. Okay, in the second case, we will get the not a constant error because 5 is an illegal index. We can also see that perhaps you've already seen standard compilers which are increasingly getting const expr support. So this moves forward with us into this world of reflection as well. We can see a std array. Std array is fully const expr friendly. It's a std array of meta info. We're putting it a bunch of type reflections in there. And then we apply the ranges transform to produce the sizes of each of those types, and we wind up with an array of sizes. It's, we use citad here, but it's presuming, no, we do it explicitly. It's an array of size t, as you can see. Now, oops, damn. I knew I'd get it wrong at some point. How are we? I think it was this. Okay, so what we have here is actually a const expr function. The reason is that we are here producing an actual function that would be available including at runtime. One of the prevalent expression examples, how to generically translate enum values to string to get the names of those fields. So we can see here template 4, which means this will be unpacked at runtime over all the possibilities. At compile time, we get this via enumerators off, that this is a reflection API. And it will be expanded, and we return the string with the identifier off, which is yet another reflection API, of course. And we can use it as simple as you can see here. Now, about that discarded candidates, and this slide is all I'm going to talk about it. It was discarded a few years ago. The idea was to have a template-based type hierarchy, much easier to use. Of course, object-oriented. Other than the future problems maintaining it in light of expected language changes, it would also quite likely generate long build times because it would create template types for any such result which will result in a template, and those templates cannot be discarded by the compiler and needs to keep them until it finishes compiling the current translation unit, unlike a variable, of course. So, the questions that I would be asking at this point is can reflection be used to re-implement both existing type traits and of course new ones going forward with reflection and without any non-portable stuff. So now we come to the proof of concept I implemented. If you want to access the Goldbolt link, this is your way of doing it. I prepared this back in February, where Copilot was just getting good enough to be able to provide me with a basis. Because as I said, reflection is not that user-friendly yet. So it gave me the kickstart. I still needed to work quite a few more hours just to get it to compile, to get some high-quality tests, and to ultimately provide Copilot with the fully correct code, just in case it's able to learn anything from it and being handed back of course, yet another version of broken code. That was nice. And as to the POC itself, at this point, there's not really much I can tell you about it because you've already seen everything. It's very basic because most of these things are quite, pun intended, reflected in reflection. It's very easy to implement that via the techniques we've seen. We can see, let's say, is void here. Uses reflection is same type to compare to void. In other cases, is exactly the same thing. We can see is integral uses something in reflection called is integral type. All these things are used via is bool constant, via stud bool constant. We've seen all those methods. And this is the second slide about the POC. Again, it's very simple. Here, this is a transformative ones. So I just do a simple type alias and employ the reflection, do a splicing, and I'm done. So can we? Probably yes. Now it remains to be asked whether we also should. Of course, worth looking into, which I've been doing. This is presumption of my part. I haven't done measurements because I don't think it would be much worth as long as those are still experimental compilers. But I think in a few months they will get to the official supporting point where it would be worth doing those measurements. But I do think that at least in the case of the template-based type traits, compiling this kind of complicated template code must be slower than something which is straightforward. And in case of reflection, it will typically be one layer deep, just one template calling one built-in and you're done. Although that one layer might be just ever so slightly slower than using intrinsics directly. Again, this is my guesswork here. We've seen what trivial code looks like in all those cases, and this will be covering lots of it, and this would be where I'd be starting. This is a low-hanging fruit, indeed very low-hanging. And another issue, another motivation that I'm seeing is that right now, we would have in C++26 two sources of truth. If you need a type trait, you can use the classical ones, or you'll be able to use the reflection type queries. I would presume that they would be ultimately implemented via the same code, but there's no way of knowing that for sure. And the standard will never guarantee that because the standard always refuses, WG21 always refuses to tell implementers how to implement. So could one of those implementations have a bug or do something somewhat meaningfully differently? I wouldn't want to live in that kind of world. And that's why we like to cut down on DRI, on don't repeat yourself as much as possible, and do things in terms of one another. So we've seen that type traits are, in most cases, even in the MSVC case, most of them are implemented via intrinsics or built-ins. But there are still many cases where we need to do all that template trickery and have very complex code. We've seen that we have value-based reflection coming in C++26 with the limitations that hopefully will, very few of them will remain in C++29. I'm especially hoping for code gen and reflection of our expressions. And we've seen there's lots of overlap between the current standard type traits and reflection meta functions. I guess we can call them that now, especially as they are indeed in the stud meta namespace. And why not use those rather than both intrinsics and templates? So, going forward one more step into the more farther future, could this be a starting point for ultimately cutting the chain completely between compilers and standard library implementations? Now, to start off, in terms of the meta header, it will have to be, its implementation can't be portable, only its API. And it might not be the only one, but that's fine. It might have to use some internal utilities that don't refer back to reflection, so do not have issues with cyclic, include cyclic dependencies. And there is an example of meta implementation, the Bloomberg example, if you want to look at it. If I remember correctly, it doesn't depend on anything else. By the way, so is my POC. My POC only includes the meta header. That was the stated goal. So, reflection, cutting this cord in the type traits implementation would be a great start to ultimately cutting off the entire cord. It's a big part of it. By no means is it the only part. Why would we want to do that? In many cases, I mean, I've worked at places who use multiple ISPs because if one of them has some issue, you don't want to be stuck without internet. So you might want to combine one compiler with some other vendor's standard library because now with, for example, contracts coming in, who knows who's going to implement contracts first in a compiler, and perhaps their standard library implementation is not the best one. And you might want to mix and match stuff. And additionally, in terms of only reflection, there's the single source of truth problem. The way I see progress, and I estimate this should take probably at least a decade, would be to gradually form a layer of headers which, same as the meta header, would be expected to be implemented in a non-portable way. All the other ones will have to be implemented in a portable way, at least to provide such an implementation with an if-def if they wish. But such a portable implementation would have to be provided. This might require some fighting inside the committee because, as I said, the committee doesn't like telling tool vendors how to implement, but I think this would be a reasonable ask. And again, the disclaimer, these are my opinions. But I do hope to hear from people, starting with you, about whether you would see this as a welcome feature that you think would be worth the committee's time, and use that as input to motivate the committee. So thank you, and see you some way or another in the future. Thank you.
Wouldn't compile times in general be much worse if you had to include the meta header for all of these standard headers? So if you implemented most of these tools using the meta, that means you have to include the meta in all of these places where it otherwise wouldn't be used, and that would also increase compile time.
Yeah, but meta itself, as I said, to the best of my knowledge, doesn't pull in further dependencies, and it has very shallow templates. So, and I have a feeling those would also be optimized ultimately with precompiled headers or with modules or what have you. So yes, as I said, in some cases it might slightly lengthen build times, but if you have lots of template-based implementation, which you would be replacing with this, then overall you would get much better build times. Again, I'm saying this at the moment without having measured this.
Thanks for the interesting talk. I have a question regarding your samples for the enumerations, because the solution there was with the if statement, if I remember correctly.
Let's see if I can get back to it.
And regarding performance, I have a question. Is it actually the same if I would do it with a switch statement?
So first of all, which slide was it?
Where you had that meta over all the enumerations of some.
This one?
No.
Member number?
No, later.
This one?
Yeah, this one, okay. Yeah. Mm-hmm. And here you create actually an if statement for each enumerator of the enum, right? So actually it would generate code where you have a couple of if statements right after each other?
Yes.
Correct?
Yes.
And is that the same regarding performance if I just have a switch statement over the value with some case labels for each enumerator? Is there a difference?
I guess not, but then again, why not re-implement this and put in that switch statement? Well, would it work with a template 4? I'm not sure, but I think perhaps creating a map would work, which is also another way of doing that.
My question is just, is there a performance impact in doing it with a couple of if statements in comparison to have just a switch statement over the value? Okay, then...
Possibly.
Okay, so the compiler is allowed to okay, if the compiler is allowed to do that, then yeah, but I wasn't sure about it.
Yeah, why not? But the idea here is that at least this example, it's not about performance. It's about code simplicity, code deduplication, no DRI. It's much easier to write.
Yeah, of course, yeah.
And it's more maintainable. You add a field to that enumerator, there's nothing for you to do here. You're done.
Yeah, from that perspective, of course. I just had in mind if there is a performance impact on that. This was my question, actually.
Might be, but it's not about that in this example.
Okay. Yeah, okay, thanks.
In the same vein, I would ask, is it possible to start the switch outside the template 4 and put the case labels inside the template 4? I don't know, that's...
The template 4 creates a repetition of those statements. If that repetition creates a valid syntactic construct, then it would work. I think Template 4, yeah, it should work. You put the switch outside, and then you put one case inside. And now the template 4 introduces a break. I'm not sure if that works, but it's worth trying, yeah.
And then my actual question, it's very, very real, this question is, why did they do the double brow operator and not just use one of the emojis, like a mirror?
Why not use an emoji?
Yeah, or the reflection emoji.
Okay, I think I'm not going to answer your question in that form, but I will answer. I refer to some ambiguity. If I remember correctly, that was about Objective-C, which has those carets. And it's used, of course, in conjunction with C and C++. D too? Might be. Probably at some point even C# came into the picture. All the guys doing non-standard stuff are screwing it for us, basically. But it's funnier this way. Okay, thank you.